Homework 19, chapters 5.6, problem 5, and 5.7, problem 2a. A cantilever beam is loaded by a uniform load Q and a concentrated load P, as shown in the figure. If it has to carry a load Q, P, and has an allowable normal stress, what is the most economical steel C-shape from table F3a? So here's table F3a. It gives us a lot of information, but really all we need to care about is the weight per foot and the S value. The S value is a function of our moment and our stress, and our moment we can just solve by looking at our little system here. We have a Q going along the whole face, a P at 3/5 L away from our M, and we also need to recall that we need to include the weight of the channel itself, which is why we are looking in this chart. So I'm going to not so randomly choose this channel section here, and the S value and the weight per foot, I can plug my weight per foot in my W here and find that it creates a moment of 4.5 kip feet. And then when I divide it by my sigma, and make sure to watch your units because there's a couple units here that are changing on us, we're going to get 3 inches cubed, which is less than the maximum S capacity of this channel. So this works. However, we don't know if it's the most economical, because as we go up, they're more strong, and as we go down, they are cheaper, because it's just cheaper to make less strong channels. So we're going to try the one just under it, so the C12 by 30, which will give us 4.3 kips. We divide that by our allowable stress, and we're going to get a value that is less than our S capacity. So this isn't maybe the most intuitive thing, because nothing in the problem statement suggests this, but for part A, you're going to use the S for axis 2, 2. Part B, you're going to use the S for axis 1, 1. And then part C, you're going to use the S from axis 2, 2 as well. Anyways, for part A, you get the C15 by 33.9, since the more it ends up being the most economical channel that is also strong enough for our needs. And I don't want to do this 2 more times, so I'll let you do the exercise and I'll tell you what the answers are, and you can compare your work and see if that's what you get. A tall signboard is supported by 2 vertical beams that are thin-walled and tapered. The beams can be modeled as cantilever with a length, a force P that they have to hold, and they have a average diameter at part A and B and a constant thickness. Due to the thickness and the fact that we're using a thin-walled approximation, we have this I, which is given to us, and an S that's also given to us. At what distance from the free end does the maximum bending stress occur? What is the magnitude of that bending stress, and what is the ratio of the maximum bending stress to the largest stress at the support? So it's asking a lot of questions about bending stress, so we can already know that we're going to be using this equation here, because I is given to us, Y is our outer diameter divided by 2, and M is just going to be that P load times our X distance, because it's going to be as a function of X, so we can't just multiply it by L. We can plug all of that in and get this. This is what it simplifies to. I didn't have it all written out and then simplify it. This is what it simplifies to. So our diameters. Our diameters are also a function of X, and we're going to need to know that information before we can start solving for our location for our sigma max. So here is a graph. So if we have point 0, our diameter is dA, and if we have point L, our diameter is dB. And I need to find this line so I can make it a function of X. So I can say if I take my D, which is my function here, and I subtract dA, my constant, you can imagine that entire line shifting downward by dA amount. So now it's going from the origin to dB minus dA. So that means if we have d minus dA, it's very easy to model that graph because it's just a straight slope from the origin. So d minus dA, which is our new graph sort of, is going to equal our rise, which is dB minus dA, over our run L, multiplied by how long it took to get there. And that's just going to be our x distance minus nothing because we've shifted it. So we can simplify that, and then we have our 2 dA over L times x. We can add dA to both sides, and then that is what we are plugging in to our sigma equation. Now it's still asking, we have sigma as a function of x, and we need to find the maximum bending stress. Hopefully what you're thinking right now is I need to take a derivative. Oh, of course, simplify it too, so you're not looking at that nasty thing, because we're going to be finding a derivative, and if we're going to find a derivative, we're going to want to have a less nasty equation to work with. So if I'm going to set my derivative to 0, I can pull out my constants, and conveniently, because my constants have no impact on locations, I can just delete those because you're going to divide it by that anyways, and when we have a 0 on either side, it just vanishes. So we're getting a derivative of this nice little x over L plus 2x squared. This is the derivative. If we're going to solve for for x, we can multiply both sides by L plus 2x cubed, and that vanishes. So all we have, the only thing we're looking at is negative L plus 2x equals 0. And so we simply get x equals L halves. Beautiful and easy. Now to find the magnitude, now that we have the location, we need to plug that location into our sigma equation that we have, because that's sigma as a function of some location, and we'll get our maximum stress. And then we also want the ratio from the maximum to the largest of the support. So we need to find the support, and the support is located L away from our origin, so that's where we're going to be plugging in this time, which gives us this. Now if you look at our two equations here, we can numerically solve for it. Just plug in everything, and then divide my sigma sub m divided by sigma sub b, or I can just look at this and say, those look pretty similar. We have pi t dA squared on the bottom and PL on the top. The only thing difference is this 2 and the 4/9. So I can just say, oh, well, if I take the top one and divide by the bottom one, symbolically, I already know that my sigma sub b is going to be 8/9 of my sigma at L halves. So it's just, if I just invert that, because I'm doing sigma max divided by sigma b, then I get 9/8 is my ratio. There's no new concepts or equations that I could think of for this assignment, but I'm sure there's something. So if you have questions, go and feel free to reach out to your TA. We'll always be here, and good luck.